If you're just joining us, good afternoon, good morning from the UK. We'll be starting in a couple of minutes. We've got more people joining. I can see the numbers going up. So we will kick off in a minute or two. Okay, we'll just give it another minute. I'll wait for the number of participants to even out, and then we'll get started. Okay, just a few more moments and we'll kick off. Okay, good afternoon and good morning from the UK. This is another training session from the ARM School Programme in association with CBSE, and we're delighted that you're able to join us this afternoon. So today's session, Introducing Physical Computing and Project-Based Learning, will be very much a deep dive into what project-based learning, what it means, how it can be effectively implemented, and the benefits of applying it with physical computing in the classroom. We'll talk a bit more about that before we reach the main session, what the purpose of the session is, and how it might help you as teachers. So this is the agenda for today. I will give a brief introduction to the school programme at ARM. We will then have the main session, which will last about an hour, and then Q&A with myself and my colleague Rob Lehman, who I'll introduce shortly. I'll then hand over to my colleague Surya to cover feedback for the session, and then we'll close. I think the session's probably going to last around about an hour and a half, maybe a touch more. So just a couple of housekeeping points. In terms of certificates for attending this session, certificates will be emailed out to attendees when the session closes within a day or so. So you will receive those by email. Another point, just through this, throughout this this session, if you could type any questions that you have into the Q&A box, that allows us to monitor questions and make sure that we're collecting them for the Q&A session at the end and responding to them. Okay, let me move on. Okay, so I've got a message here that I'm not audible. I trust that the majority of you can hear me, and if not, please do. I'll allow my colleagues to raise that. Okay, so welcome. This is, as I mentioned at the start of the meeting, a series of training sessions for school teachers, principally aimed at teachers who have some level of involvement in computing. So you may be from one of the STEM subjects, teaching one of the STEM subjects, or teaching computer science itself. I'd like to start by thanking CBSE for this opportunity to work with them. In particular, thanking Dr. Saha and Mr. R.P. Singh for their support. And really the purpose of the series of webinars that we're running is really helping you as teachers in encouraging, eliciting, developing the skills that your learners will need for what is a very fast evolving careers market, a job market. So that we know that the jobs of tomorrow, they are, for a large extent, they're going to be very, very different from the landscape for careers today. And we know that to prepare students as best we can for those jobs, we need to look at the kind of core skills that are transferable across a number of different disciplines. And we're talking about skills such as STEM skills, things like creativity, resilience, teamwork and communication skills. And it's our program is very much around suggesting methodologies for eliciting those skills in your learners as part of your tool set as teachers. How can you appeal to your learners, to a broader range of learners who are going through studying computing, studying STEM, and how can you help them in developing those STEM skills? Your speakers, I'm there on the right. My background is very much from an education perspective. I've been with ARM for about 4 years, working within the education team, which focuses on both schools and universities. And I'm joined by my colleague Rob Lehman, who will be running today's main session. Rob, would you like to say a few words?
Hello everybody, and thank you for joining us on today's session. As you can see there, my background is very much in computer science education and curriculum reform and assessment. And since my time at ARM, I've been working with Nick on honing our approach to physical computing and project-based learning and using it as a tool and a pedagogical approach to better teach computer science and also to inspire and engage young learners into the world of STEM.
Thanks, Rob. And as I mentioned, Rob will, as a former computer science teacher and trainer, will be running the main session today. Okay, so a brief introduction to our school program. As I mentioned earlier, really the purpose of what we're trying to do as ARM with working with organisations like CBSE is, as mentioned here, so to empower all learners with the opportunity to develop the interest, knowledge and skills that enable a lifetime of engagement in STEAM, whether these are learners who go on to work with technology companies like ARM or our partners, or whether it's simply about ensuring they have the understanding that they need in order to effectively function within society as technology develops. So it's really thinking about the students as a whole and their engagement with the modern world. Our school program is founded really around support for teachers. So we work with organisations like CBSE to support teachers in their classroom practice, people like yourselves who are looking to develop the tool set they have available to them in delivering inspiring lessons to students. So we provide professional development, including on edX, and you'll have seen that on the registration page, that there are courses that we produce, and I'll talk a bit more about those in a moment, that are free to access. We also have a range of free to access curriculum linked resources on our website. We have, which is listed there, so school.arm.com, and you can visit that, explore it at your leisure, and also sign up to our newsletter, where you'll receive regular updates on new content and new training opportunities. And this is the program. So on the platform edX.org, you will find a program called Teaching with Physical Computing, which comprises 4 courses, which really explore, this is for teachers, professional development for teachers such as yourselves, and they explore in detail that this combination of project-based learning and physical computing in the classroom. What do you need to know as a teacher, as an educator, both from the educational theory perspective all the way through to the classroom practice, in order to facilitate effective lessons within computer science. So, as Rob will go on to explain, project-based learning is a broad term which is often very poorly understood within teaching, and we have a very particular take on it within the school program that is evidence-based and also enables learners to both develop the skills they need within the curriculum, but also in parallel develop those STEM skills that we've referred to earlier. So there are 4 courses there, and you can sign up if you haven't done already. And the training sessions that we're running with CBSE, you can see them listed here. There are 7 in total. The first one was Get Started with Physical Computing. This one running today, and then we have 5 more coming up over the course of the next 6 or so months. And these webinars really draw on the topics that you would find within the edX courses and explore them to a certain extent. But if you want to do a deeper dive, we'd certainly encourage you to sign up to edX. So today's session is the introduction to physical computing and project-based learning. Next session, which is on the 23rd, is about a key part of project-based learning, which is how do you develop contexts for projects that will interest and engage your learners. And this really is a foundational part of the effective project-based learning in the classroom. So looking at the things that are going to inspire your learners, motivate them to solve a problem or a set of problems within a particular space. So how do you do that? Starting from a blank sheet of paper, and that next session is going to be a great guide to that process. And then you can find more details about future sessions on the community site. So that's community.arm.com/ASP-India, which I think will be where you will have found the registration link for this session. So there's short explanations of those future sessions on that site. Okay. So we now move to the main training session, where I'll hand over to Rob. This will last for about an hour. As I mentioned, just repeating the housekeeping points. If you have any questions, please do put them in the Q&A box, which we'll monitor over the course of the session, and try our best to cover any questions asked in about 20 minutes after the main training session. And also, if in terms of access to certificates for the session, those will be emailed to you to all participants after the close of the session. So that will come in the next couple of days via email. Okay, let's get started. Over to Rob.
Hello and welcome to the ARM School program's Introducing Physical Computing and Project-Based Learning. In today's session, we're going to take a deep dive into the theory and practice that underpin this pedagogical approach. As we looked at in our last session, here is the broad map of different areas and concepts that you need to understand to effectively deliver project-based learning and physical computing. And we're going to be looking at some of the theories and constructs that underpin all of this and seek to explain how it all works and how it all fits together through the context of learning. So this really forms a part of the PCK, or pedagogical content knowledge, and in the last session we looked at sort of the nuts and bolts of physical computing and how to use specific physical devices such as the microbit, and in this session we're going to focus on the pedagogy, the practice and the theories and research as to why these are effective tools to use. So let's get started. So we'll start by looking at this diagram which covers all of the different theoretical and practical elements that we will describe as part of project-based learning and physical computing. And you can see that we start off with the theoretical elements at the bottom, and today we're going to be talking about the big three orthodoxies, which is cognitivism, constructivism and behaviorism, and how they sort of connect together and form what we understand to be project-based learning and physical computing. And because there isn't just one practice or paradigm that explains it all, it's a collection of all these different theories and how they're applied through practice and practical applications and in different weights and measures to make up what project-based learning is. And there are various sort of teacher-centered and learner-centered pedagogies that you can apply these through. And all of this sort of together makes up how we see project-based learning. And all of this is gone through in lots and lots of detail in our edX course, where we go through all of these different elements and how they fit together. But today we're going to focus specifically on how learners learn and through cognitivism, and what they learn through sort of the constructivist ideologies, and how the behaviorists see these changes impacting students, and how you can observe these through their behaviors. So the first paradigm that we're going to look at is that of behaviorism, and it's one of the learning theories which underpins sort of cognitivist and constructivist learning theories. It's probably best known as in its application of conditioning that Pavlov demonstrated through his work with the dogs, where he would feed dogs and then ring a bell at the same time, and then that conditioned the dogs to salivate or react to the expectation of receiving food. And he demonstrated this by then ringing the bell and the dogs salivating without giving them food. So there was that link between the presence of the bell and then the salivation. And we can see this in education through operant and as well as classical conditioning, and how behaviours can be modified by applying sort of behaviourist concepts. And so this how this links to sort of project-based learning is repeatedly exposing students to situations such as problem solving and the need to be resilient, and applying different tools and techniques, and then through repetition you can condition students to behave in certain ways when given computational or other STEM problems, and getting them to solve them. So this has various pedagogical tools which you may already have come across, such as modelling, where certain behaviours or practices are modelled by a teacher or a peer, and then other students can see that being done in a certain way, and then will learn through that. That's effectively behaviour modification. Another one of the big constructs is cognitivism. And again, this links to behaviorism and constructivist theories, and it was demonstrated mainly through Piaget and Bruno Novak. And it tries to describe the process of how they learn and how they process information, and it goes from sort of thinking and knowing and into memory. And this is best exemplified through Bloom's cognitive domain, and also the Bloom's taxonomy, which we'll look at in just a second. But effectively, it's this idea of how learners approach certain problems, and how they go from sort of basic interaction through to more complex interactions, and through applying different pedagogical skills such as reflection, discussion, exploration, etc., and how that can sort of solidify and make concrete what teachers are trying to teach their students. So the criticisms of this is that it's not something that can be observed directly, although you can often see this in practice where students are learning, but it's difficult to measure empirically, and it is also quite reductionist in its approach, and you have to, it's more sort of qualitative than quantitative in terms of it's how you can measure it. But I think lots and lots of educational material does use Bloom's approach and Bloom's taxonomy, and it's a scaffolding which seems to work in educational institutions all over the world. So let's have a look at that for just a second. So this is a good demonstration of the different concepts, starting with sort of knowledge and remembering and recalling different concepts. So just the simple act of recalling something is sort of seen as the lowest end of the spectrum, and you can see there's some words there that are typically associated with in assessment as well as learning tools. And then we're going through sort of comprehension, sort of just understanding, so going from just being able to recall to fully understanding a fact. And then being able to then apply that knowledge in a novel situation. So that's seen as applying more higher order thinking skills, and then analysing, sort of seeing new and novel situations and be able to apply analyse how that previous knowledge could be used in a new situation, and then synthesising that. So again, having problems and being able to come up with novel solutions to that through analysis, application, comprehension and knowledge, and eventually be able to make and defend judgments through that, so being able to fully understand what a concept or a practice is. And so you can see this process is one of the core constructs of project-based learning and physical computing, because we want students to be able to go through this process of, through knowing, comprehension, application, analysis, synthesis and evaluation, whilst they are trying to solve a problem. They'll go through this sort of multiple times, so they may know how to use a particular construct in computing, for example, like a for loop or something like that, or they may know how to use a battery pack, but do they know how to do that in a more complex situation? And so you'll see them going through this process of applying previously learned knowledge and using that to figure out how to analyze a problem and apply that knowledge in novel ways. And that's kind of this is part of this learning journey as part of project-based learning. The next theory we're going to look at is constructivism, and this is best typified by Vygotsky's zone of proximal development, which we'll look at in just a second. But this links in terms of theoretical constructs to behaviorism and cognitivist and constructivist theory, and effectively it's learners constructing learning through experience, and so it's an active way of learning, and the idea is that you learn by doing. And it's so you'll be given a task, and then through the act of interacting with that task and solving a problem and then reflecting upon it, that's how learning occurs. And it takes this idea that students have this sort of pre-existing schema, and then they will be given a problem or a task, and then they will apply their pre-existing schema to that, and through doing so they will assimilate what that problem is and make that part of their understanding as a whole. The way to use that as a pedagogical tool is to challenge learners in a specific way, so that students don't become disengaged, but you're stretching them enough so that they are challenged and have to think and have to sort of rethink about how they see the problem or see the world in a way that helps them learn. And this links to project-based learning in terms of how you craft the projects and the computational problems in a way that are not too difficult, and that they have the appropriate amount of scaffolding, so that students are stretched in an appropriate way. And it's criticised as moving away from sort of didactic approaches, of the classical way of teaching in terms of standing at the front and chalking and talking. And whilst that is levelled as a criticism, I think that's probably a good thing, because that's the whole point of project-based learning, is that it removes students from this sort of purely passive role and into them building things and creating artifacts, and learners really building a solution to a problem. And you can also couple this with other pedagogies, such as the Socratic approach of asking questions and interrogating learners and getting them to justify and think about what they're doing as you're going through. And this is one of the core practices of project-based learning. And this you can't take constructivism in its sort of classical approach where learners are just learning by doing, and that is all with no interaction from the teacher. This has to be coupled with appropriate scaffolding and appropriately designed problems, so that students can engage with it initially. So it's with it in a context which they understand and they're familiar with, and they are given resources and material to help stimulate their learning rather than just being left to discover the learning by accident almost. So I think there's a balance between sort of the pure constructivist approach and project-based learning, where you will give them a little bit of a helping hand to make sure that they're on the right sort of path. And so here's a diagram that kind of explains the zone of proximal development. So they have the learners at the beginning of the lesson, so what they understand, and then in terms of stretch and how you can sort of eke out the most learning from them. It's this idea of this what they can't do and how you get to where they can do it. And so it's about scaffolding the learners, or scaffolding the support material that you offer the learners in a way that stretches them in the most efficient way possible, so that they will actually get to where you want them to be. So it's almost creates a sense of uncomfortableness in learners, insofar as you're challenging them and you're giving them things that they're not easy and so that they have to make sure that they are doing something to kind of earn their learning, if you will. And it's this concept of constant keeping them in this zone of proximal development constantly, so that they are constantly moving forward. And that's why we use things like stretch tasks in the ARM School program schema, so that students that do find the initial success criteria easy, then you can stretch that learning out further and you can get more out of them. So that it's almost sort of differentiation through the success criteria and the stretch tasks, and it's keeping students so they're constantly progressing in the right direction and not veering too much off course. And you can use this through either the computer science applications, so giving them more complex algorithms to solve, or giving them more complex hardware to play around with as well, so giving them additional modules and inputs and outputs and that sort of thing. So there's lots and lots of different ways to stretch learners in project-based learning and computation and physical computing, simply through the application of the hardware or the task itself. So the next theory we're going to look at is constructionism, and again this is something we've sort of mentioned previously in terms of learners actively constructing their learning through engagement. And this is this idea of sort of discovery learning, and this is something which we sort of almost rubbished in the previous slide on constructivist approaches, where learners, well, the idea is that learners do just kind of learn by doing and sort of learn through osmosis, through the act of creating worlds or learning. And the criticism of this approach is that it's not just a theory, and you can't really measure it empirically. But I think all teachers see this in the day-to-day classroom, that learners do learn through interacting with tasks and they can learn effectively through solving problems. But again, in and of itself, a typical learner in a typical classroom isn't going to learn most efficiently just through dealing with projects and tasks. There does need to be some additional thought about how each learner is helped, and the other support material is scaffolded appropriately, and how you reinforce the learning. And it's really important to make sure that there's this element of differentiation through your pedagogical approach. The good thing that we can take away from this in terms of project-based learning is one of the pedagogy. So it's people do learn through making things. There is something to be said. I think we can all appreciate this. Is that when you try to do something new for the first time, obviously you'll do it badly the first time. You'll fail early and fail often, but you do get better as you go on, and you can speed up that journey through effective support materials and through well-crafted learning experiences. And that's what we try to do in the ARM School program materials, is to give problem sets which are engaging and accessible, and steer the learners to learn things that we want them to learn, and also create these artifacts at the same time. And I think that's part of a central part of this, is that learners, by making something, they are learning how to do a particular thing, but we just have to be careful and cognizant that we are designing problems that get the students to do something that they want them to do. It's not just a completely Wild West. It has to be authentic, and the learners have to take ownership of what they're doing. And ideally, they have to be sort of iterating on a problem whilst programming their artifact to do what we want them to do. And so you can see how this is expressed through the success criteria and the stretch tasks that you can see in the ARM School program material. So one of the criticisms levelled at PBL is that is it just constructionism and is it just constructivism, and where does it sit in terms of them, and are they indistinguishable? And they are different in terms of theories. It's the sort of the how and the why, but it's really a sort of a combination of both with a load of extra stuff added on to make it more effective. I mean, I think project-based learning as a pedagogical approach is less didactic. It does require contextualization. But it does use that constructivist approach of learning by doing. So there is this idea of the sort of kinesthetic learning, or learning through interaction with the problems that they're doing. I think the limitations of it, it's not just the doing that does it though. It's not just the creating of the asset which yields the learning. It's also with the piecing together of different concepts and constructs to solve a particular problem, and then doing it again in a more complex situation. So doing a single project will be useful and will be fun and will be engaging, but you have to do these things over time, and you have to ramp up the complexity of these projects to cover the curriculum effectively over a number of lessons. And project-based learning is sort of seen as a sort of an event, like a one-off, when really it can be an effective pedagogy to apply across a term or a year, and but you just have to make sure that you are covering everything that you need to cover across that time. Not saying that you can replace your entire pedagogical approach using project-based learning. You may need a little bit of didactic, just a sort of chalk and talk to cover some of the other areas of the curriculum that aren't best explored through project-based learning. But it's a really useful tool to explore and teach and learn all about the more sort of practical elements. And I think one of the limitations of it as well is it sort of assumes learners are really engaged all of the time, and that's again some of the same sort of criticism that can be levelled at constructivism and constructionism, in that it assumes that students are going to be completely emboldened and want to go and learn all the time and aren't distracted and don't have problems. And as we all know, students, are human beings. They all have problems. They all have other things on their mind, and so that's why we need to really ramp up how we engage learners, and how do we enthuse them, and how do we create projects that are not just exciting for the students to want to try and solve, but also realistic and achievable and have sufficient support material. And that's a crucial part of how we see PBL. It has to have all of this dressing around it to make sure that learners can be supported in an appropriate way, and we can eke out every bit of progression that we can out of that individual learner. And again, that can be done individually, or it can be done across groups or across classes, across year groups, but it has to be thought about, and you can't just assume that learning is going to occur by accident. It has to be designed into the projects that we look at. And so the physicality of it is also really, really important. I mean, in the sort of the constructionist approach of thinking about this idea of creating artifacts and creating things that students can learn from. This links to research into other thinking systems that you see this a lot in STEM subjects, such as engineering, and that it's this idea of an engineering mindset. And I suppose you could have a sort of a computational thinking mindset as well. And it's just a way of looking at problems and systems and deconstructing them and decomposing them that normal people don't typically do, and it's a way of thinking that we have to train into them. And through project-based learning, we see this sort of adoption of the engineering mindset, because you're giving them a physical problem that does involve computation, but also has an element of physicality that they need to untangle, decompose, deconstruct, and engage with on a sometimes quite technical level. And so they need to think in this way, and they have to be able to design solutions to interesting and novel problems. And whilst the problems might be simplistic at first, you can go quite far in terms of the complexity, and you can see this with some of the project-based learning projects that the Arm School program has, and it goes from something as simple as the micro pet all the way through to more sophisticated robotics projects like the oil spill cleaner upper and the tree protector, and all the slew of other Pico-based projects involving like data science, and also trading into like computer vision and even machine learning and artificial intelligence. So you can ramp up the complexity of these products really quickly should you wish to. But the idea of that making something and having that artifact is really central to project-based learning, and it's something that students can make real. And I think this is also really another interesting theory to consider as part of project-based learning is Kolb's learning theory, and this idea that they or learners need to have this concrete experience. So they have this experience of a project or a problem set that they need to interact with and that they encounter, and then as part of that they need to observe and reflect on this new experience and think about how this problem set relates to previous problem sets that they've encountered, or previous theories or skills or practices that they need to apply in all of this, and where the gaps are in their understanding. And then this leads to sort of the abstract conceptualization, where as part of this reflection they see this new idea or this modification of an existing abstract concept, and then they can start to see how this relates to this pre-existing schema that they have of this concept. And again, this is why it's important to build out problem sets that sort of use this idea of spiral learning, and so that you're introducing new concepts and practices and problems over time, and that they can learn from previous working projects and apply them in new and novel situations. And then as they're doing this abstract conceptualization, they then can start to actively experiment, and then they can apply previous ideas and new ways of thinking to solve this problem. And again, this is all can all be done in an abstract sense, or can be done in a sort of a physical sense as part of a project-based learning experience. And you can see this this cycle happening multiple times when learners are engaging with the problem set which is new to them. And as mentioned previously, they might have used a servo motor before, they may have already used a particular programming construct, but in a novel problem set, this can be quite difficult for some students to unpick. And so by thinking about these things in this way and introducing different problems that need the use of different programming constructs and different physical practices, we can inspire learners to express themselves creatively whilst solving problems. Another theory that loops into all of the project-based learning landscape is this idea of semantic waves. So you can see there's this sort of wave diagram where the name comes from, and you start off a learning experience such as a lesson or a project with a sort of a high density concept, sort of this is what you're trying to do. So this is the idea of setting the scene or unpacking the context of what they're trying to do, and in and of itself this might seem inaccessible, or it might seem an impossible problem to solve initially. And then that's why it's really important to have these scaffolding materials explain to students how they can actually unpack these terms and these abstract concepts, and then seek to make real these problems, and then look at ways to actually solve them using the tools that you're giving them. So here you can see their sort of as part of the learning experience should be unpacking, sort of explaining the concrete things in simple language. So this would be your success criteria. So they know exactly what the problem set is, and they need to start thinking about how can they actually solve this using the tools that you're providing them. And you can see there, there is use this idea of this unplugged activity, but that can also be a plugged-in activity in terms of using physical boards, using additional peripherals, and this is where they're doing and they're creating a solution or an artifact that solves the problems that you laid out for them in this abstract way at the beginning. And so this is why the problem. This is why decomposition is really, really important. So and you can do that partially through the success criteria, where students are given this sort of list of things they need to do, and they can work through them one by one in a fairly low density environment, so it's easy to understand the individual bits. And then towards the end of the project or the end of the lesson, you can start to link back how all of these different elements and different problems that they've been solving all coalesce to solve the original problem that you gave them at the beginning of the session or the beginning of the project. So this is the sort of the learning journey. You start with something which is a big picture, so we're going to solve an oil spill, let's say, and then you go into all of the different elements that make that up. So you need to make a robotic boat drone that can go around and mop up this oil. And how do we do that? We need to make sure that it can work at sea. We need to make sure that it can tow something. And this is an example of a project that we'll look at later on. But it's essentially something complicated. We break it down into lots of simple steps, and then we repackage it to show students that the journey that they've just been on in terms of learning, and how they've pieced together all these different elements to make an artifact which solves a real problem, and what they've learned along the way. So I think this is a really interesting idea about how to package project-based learning in a way that students can first of all engage with and do some complicated stuff, and then linking back to using sort of reflective exercises, how they've solved these technical concepts and these abstract ideas. Another useful tool which is really popular in the UK is this idea of PRIM, and this is particularly useful for project-based learning, as well as just learning computer science techniques and concepts initially. So it stands for predict, run, investigate, modify, and make. So for example, you might, in project-based learning, use this as part of your questioning techniques. As you're going around, you would get students to predict what an algorithm would do, and you could use this in terms of some partially constructed solutions that you might provide learners, or it could be a way to get some stimulus material that you might give them, and so they would be predicting what a particular algorithm would do, or you might get them to predict what the outcome of a particular problem set would be if you did it in a certain way. And so it's a really nice, easy way for students to engage with what might seem at first to be quite a complicated problem, and it allows them to sort of take ownership of what they're doing in meeting the criteria. And then you might even provide them with some sample code that you might get them to run, and then so they can see the code working, and again that allows them to engage with that. And whilst with project-based learning you might typically give them the success criteria and the hardware and expect them to be able to run with that, that's not going to always be the case. With younger learners they might need more stimulus. Even with older learners, more advanced learners, you might need to give them some sample code or some sample libraries, even some material for APIs if you want them to do something more sophisticated using new tools, because the more complicated this gets, you start getting into professional developer territory where they need to understand like how to use online libraries, APIs, how to use GitHub and these sorts of things. And so it's important to give them appropriate scaffolding to allow them to stay in that zone of proximal development and go far, and that might involve giving them partial solutions to certain things, or at least tipping them in the right direction in terms of where to look for the solutions. And again, that's part of this investigative part of this as well, and sort of you can point them in the right direction, but you would expect them to then go and find the solutions themselves. And you obviously have to make sure that where you're pointing them to has the solution, but that's a part of the skill of crafting effective project-based learning activities, is being able to design this learning experience in a clever way. And then modifying. Now, this might be in a traditional computer science sense. You give them some code and you get them to refactor it in some way or change it so where it uses a different technique. For example, like instead of using nested ifs, using a loop, for example, it's a classic example. But in sort of project-based learning, you may introduce the success criteria in a different way, or partway through a project, you may throw in some additional success criteria, or even one of the stretch tasks that makes or forces the students to redesign or rethink about how they're approaching a particular problem. So, for example, with our boat drone, you might say it needs to go in a straight line from A to B. And then later, and so they'd have to write an algorithm that turns the motors on so it can go forward for X amount of time. And then you might say, oh, there's a southeasterly wind. How can you make it so that the boat can stay on course? And so you're throwing in additional stimulus that makes students modify and think slightly differently about how they've solved this problem. And so that's a really important thing, is getting them to modify things that either pre-exist or something that they've already done, and they have to adapt it to suit a new situation or context. And last, there's this idea of making something, so getting them to apply these skills in anger, and that's all about this idea of creating an artifact and programming an artifact and applying these skills in a meaningful way. So if you've got students that have never done project-based learning before or physical computing, you may want to first introduce them to a microbit or a Pico or a Raspberry Pi or an Arduino or whatever, and get them to play around with these things at first and give them some sample code, give them some well-crafted examples and get them to play around with it before you get them to actually apply it to a real project. But that really depends on your learners, how old they are, how experienced they are, how confident they are, and how resilient they are. And a lot of learners can go quite far without necessarily needing to have that sort of spoon feeding up front. They can learn an awful lot, and I think this prim technique programming is really useful for more advanced projects where you may be introducing a lot of new stuff at once, and therefore you can justify giving them some sort of partial solutions or pointing them in the right direction just to speed up the learning experience, not necessarily providing all of the answers. Another theory which feeds into all of this is Asbel's subsumption theory. So this is sort of a way of representing how what we've just been talking about, really. So students having this new learning experience, and how do they add that into their existing corpus of understanding of stuff. So one really really useful diagram to look at this is taken from constructivism. So they've got this new learning that they've done through through doing a project, for example, and they have this existing body of knowledge that they already have, and then that they sort of fit together, and that's kind of how what learning is through subsumption. And the idea is that you can craft the learning so it fits into that pre-existing knowledge in a clever way, and that's when I was mentioning previously about designing these learning experiences so that it is easily subsumed. And that takes a bit of practice. So doing one-off projects, this will happen naturally, but if you're using projects over the course of an entire curriculum, it's good to think about it in this sort of way, that you have to teach it, or rather deliver the material and design these learning experiences with appropriate scaffoldings to enhance the students' existing knowledge, and then shoving in the new content so that they do learn it in an effective way. And that is really what subsumption is all about. And then one of the final ones, which is one of the core ones, one of the core methodologies or ways of thinking about the soft skills in physical computing, is Fullen's 6 C's. This is a really nice way of conceptualizing all of the soft skills. And this is why in project-based learning we typically use group work, and we get them to work collaboratively with each other. We give them engaging and real problems to solve, so that they have to think critically about how they solve them, and they have to be creative in how they solve them as well, and not just in this sort of the traditional kind of IT sense of creativity in terms of like, you know, colouring in or designing. They have to solve the problems creatively, especially when you prompt them to change their design, so they have to think about the problems in a novel way, and this is why you have some of the open-ended tasks in the success criteria, so that students can kind of attack this in different ways and come up with new and interesting ideas. And the idea of getting them to collaborate in small groups is really, really useful as well, because that fosters communication and collaboration, and it helps sort of bring everybody along on that learning journey, and sort of building that sort of sense of character and citizenship. So you know, how you structure your groups is up to you, obviously, but you know, it's nice to have mixed gendered groups and mixed ability as well, and that way everybody can sort of play to their strengths. But you just have to make sure that students aren't just taking specific roles, like one person doing all the designing, one person doing all of the coding, and one person doing all of the cutting out sort of thing. It's making sure that students have to you know, try everything, and they have to do that through, you know, collaboration and communicating effectively. And so it's a really nice way of capturing these sort of slightly ethereal skills, which are really, really important in the workplace, but are difficult to assess and are difficult to acknowledge empirically. And so you see this when they're doing projects, and you can recognize good communication and collaboration just by viewing it, but it's really, really difficult to assess effectively. And but this captures it really, really nicely. So those are some of the theoretical constructs that underpin all of project-based learning. That's not all of them. That's just a sort of sampling of some of the big ones, which I think demonstrate the efficacy in some of project-based learning. And again, it's not one of those theories is kind of captures it all. They're all sort of ideas and theories that sort of hang together in this sort of in this sort of cloud of what is the concept of project-based learning. And I think you can take learnings from all of these, and I think it really, really helps to understand these different learning theories, and then see how these can be taught and applied in real life. So just hold those in your mind now while we look at some of the practices and pedagogies, and how the ARM School program has used these to design a learning experience. And you can see all elements of all of these theories coming out through the way it's designed, and also the projects and solutions that students would come up with as part of this. So let's revisit the ARM School program schema just briefly, so that we can see how all this hangs together. And I've been mentioning elements of this throughout the talk. And so the schema is the colourful bit in the middle there. So the way that we structure all of the projects, and again, you can use this to design any project-based learning experience you want to, irrelevant of subject or context. So first of all, you have the getting started. So that's where essentially you come up with or use an existing context. It could be something that you know will engage your students, or it could be something linked to a theme in your school. You could use the global goals, for example. You could use anything at all as the context, but it's got to be something that students are familiar with, and something ideally that is as engaging as possible. It might be a subject area or a theme, or current affairs, whatever. It's just whatever's going to work with your students. And then through that context, you then have to come up with some success criteria, and these are really the kind of the learning outcomes or the learning objectives, and this is the sort of set of challenges that that students are going to be working on. This is the most important piece of the project-based learning, because these are the bits that students are aiming towards. This is the bit that's always going to be on their minds, and this is what they're going to be assessed against. And so you need to craft these quite carefully. So start simple and get more complicated as you work through. You then have this element of pro tips, sort of professional tips, which is effectively the scaffolding which you would provide to the learners, and this could be something as simple as one-liners like you see in our teaching and learning resources, or it could be worksheets, sample code snippets, it could be links to GitHub, it could be partial solutions, it could be almost anything. This is where the scaffolding really comes in, and you can apply that however you see fit, and depending on your learners. And then we have stretch tasks, which are kind of outside of the bounds of the typical project, and don't necessarily need to be done, but are used there to differentiate upwards and to challenge your more able learners, and they effectively keep them on track. So it makes the project slightly more tricky or difficult, but it makes them reinforce the learning that they've already done in different ways, and it really sort of tries to stretch out some additional understanding and some additional complexity, but still within the contexts of the project. And then finally, we have this reflective exercise. So this links back to the context to which it was originally set in the getting started scenario. And this is where we go through this semantic wave of linking the original abstract concept to what they have been doing in a concrete fashion through the success criteria and stretch tasks, and then saying, this is why you've done what you've done, and this is what you've learned along the way. And this is all expressed in lots of different formats. I think the best way to look at this initially is to look at the micro course resources, and you can see these as headings in the material throughout the course. We also use these in all of our formal lesson plans. We have a full curricula where each lesson has each of these elements in there, but the formal curricula has a lot more material to scaffold it. So for example, in the pro tip section, you're going to have worksheets, you're going to have cheat sheets, you'll have teacher solutions to all the coding problems, that sort of thing. So there's a lot more going on in there, and it's more kind of like typical teachery material rather than just being a single project. And the idea of this is that this schema can be applied to either a single hour-long project that you might do with learners, or applied across an entire year, an entire curriculum. And it can be used in lots and lots of different ways. It's very, very flexible, and it's been designed to be such. So that's the sort of the schema, and we'll explore how that is applied with all of these theories that we've been talking about in just a second. So bringing in some of the more sort of techie elements into the context, and this we've got a separate session looking specifically at how to contextualize different things, but this is a really useful one for the computer scientists among us, and this is this idea of IoT, or Internet of Things, and some of the devices that you can use to look at this. Now, IoT is still very new, which we're seeing it sort of slowly work its way into our everyday lives. We have smart fridges, smart street lights, smart phones, smart everything. And it's a useful way to teach not just IT, but also computer science and data science as well as physics, and looking at sort of the big picture of how all this stuff fits together. So you have these sort of the edge devices, such as Arduinos, microbits, Raspberry Pis, etc. And then this is where you get into sort of the more network infrastructure bit, and how does data get transmitted between a device, the internet, and then a server somewhere. And so you can start to look at the technologies involved in like gateways, and then these cloud-based applications where you can actually interrogate the data. And there's some good examples there of free-to-access platforms where you can stream data from these devices and then interrogate it online and do some interesting data science activities, and they automate dashboarding and give you some really interesting graphs. But you can do these things locally as well on microbits. For example, you can graph data, or you can store data as a CSV on the microbit and then export it and do data science. And the idea is that you can teach sort of the network infrastructure element as well as the cloud-based infrastructure, or at least the basic concepts of it, using physical computing, and then using that as a baseline, as a context for, right, let's make a smart X. And that could be like a smart city application, it could be a smart car, it could be a smart street light, it could be almost anything. You can use these sensors and this technology to explore any field you really like, really. You can apply a chip to almost anything and learn something or get something from it. And that also leads us nicely into this context of data science and how this is starting to work its way into the curriculum. And we're seeing this in the UK in the under the maths banner, and used to enhance the teaching of statistics. I think this is a really sort of interesting confluence of computer science, IT, network infrastructure, maths, statistics, and also the sort of subject domains and business world, and how all these different elements come together and contextualize how we can use data science to teach all of these things all at once. Because let's say, for example, take some simplistic examples of, let's say, a physics lesson. And then we're going to be using, let's say, a Pico, and you can get it to measure the acceleration of something down a ramp. And so, rather than sort of doing it in the traditional sense of, with the stopwatch, which is, obviously not a very accurate way of doing it, you can apply digital technology to measure what the experiment is doing in a very precise way, and then take the data off of that device and then use it to perform statistical analysis. And so you can they're using IT skills and physical computing skills to gather the data and then interrogate the data, and in doing so they're learning about IT, maths and statistics all at once, and then you can apply that to whatever context or business domain that you want to. So it's a really, really nice way of stretching students and doing more with it once you kind of got past the initial complexity of the physical computing. And you can apply this this idea of data science to almost any subject at all. If you can measure it using an electronic device, you can do data science with it, and that's where it opens the door to using any kind of context you like and looking at it through a data science lens. How could you use this stuff to teach the sciences? How could you use it to teach geography? You can take data that measures the weather patterns, for example, or for example, irrigation data from farms. If you can measure, you can do almost anything. And if you start to think about like computer vision as well, that's when you start to get into the world of using statistics and machine learning to recognize certain objects, and you can use that for almost anything. I mean, just think, for example, in a context of schools, you could, for example, have a camera in a school which takes the register automatically, using facial recognition. And how do you train an algorithm to recognize people's faces? There are pre-built libraries online that do this sort of stuff already, so it's not too difficult for students to access this through K through 12, and to be able to do proper data science and do proper machine learning and create real solutions to real problems. So it's just this is just sort of the next step, if you will, once you understand how to do project-based learning properly, and then how to really dig deeper into how to apply this in different subject areas. And then how to apply these theories as well. The really important model, which I spoke about previously, is this this input process output model. I think it's worth repeating why this is really important. And again, this also works for in other contexts, but in thinking from a sort of a systematic approach. And this links back to what I mentioned before around engineering mindset and thinking about everything as a process in terms of what data is coming in, how is it being processed, and what the output is. And so I think it's a really, really useful tool, a really useful sort of schema to look at almost everything and think about how can we take something in and how can we spit something out once doing some computational elements on it. So it's useful to have this in the back of your mind all the time as a way of getting students to frame problems. And this helps with this abstract conceptualization of projects, because you can start students with a simple model like the micropet, and then you can introduce them to more complex problems, and then once they get used to sort of analyzing it and then decomposing problems in this way, it becomes natural to them, and they will get used to applying it just like any other skill, and they'll get better at it and be able to solve more and more complex problems. And this concept of decomposition can be taken outside of a sort of system setting, and you can use it to break down like the tasks overall, so they can look at this as an entire project. So you give them the bigger picture, you give them the context, you give them the problem set, and then they have to break this down. They have to look at the success criteria. They have to think about how are they going to solve these problems. And the more complicated the problems are, and the bigger the problem set, the more they have to do this. And it also becomes more important to design a solution and apply these problem-solving skills earlier on. Students always want to jump in with both feet and start to solve the problem physically. They want to start programming and building the device straight away. And whilst that is appropriate initially to keep them engaged, the more complicated the problem set you go. Once you're sort of 3 or 4 projects in, you really want them to force them to think about how do you design this, and how do you design a solution on paper first before getting your hands dirty, for example. So it's worth spending a bit of time doing that. And also this idea of iterative development. Even if you do design a good solution initially, and you think you've solved the problem, upon sort of physical implementation, there's always going to be some elements that need rethinking, and again, fail early, fail often, and that can be quite disengaging for students. So it's important to beat into them this idea that they will have to iterate on their designs, and you can force that, as I mentioned before, through introducing new success criteria, or through the stretch tasks, things that make them think slightly differently, and that ultimately leads to the solution. The iterative development cycle, as I mentioned previously, is really important that students understand how to do this. They have to hold in their minds what the success criteria is. They have to plan and then design it, and then they have to develop a solution to it, and then the idea that they have to test what is going on. And you can do formal testing if you want to. This is sort of a hangover from classic IT and also computer science, that test what you've done and then do a mini sort of iterative cycle there, evaluate what you've done, and then go back to the success criteria. And students need to be taught how to do this. You need to be prompted to keep doing this, because they're not just going to do it once. This isn't a sort of a waterfall process where they just plan, design, solve, job done. They're going to be doing this over and over and over again, especially when they're new to this, and they're going to be tripping over different elements of it all the time. And again, and as I say, you can introduce different elements that force them to work their way through this process multiple times to make sure that they're constantly rethinking their problems. And again, this way of challenging students in this way really helps make the process of problem solving more concrete, because they're having to justify it and reevaluate and rethink about how they approach these problems multiple times. So how does the hardware fit into this? Now, let's take the example of selection, and this is like an abstract concept. You could teach this on the board. You could and you can use something like Python, for example. You can see the example there, and this is how it's traditionally done. I've seen lots and lots of teachers do this. I've done this myself, and you can sort of give them an example of code on the board. You can talk through it. You can do this in a very didactic fashion, and some students will engage with this. It's very much how maths is taught classically, but you can do this in a much more effective way, which is much more engaging. And that's you can see some blocks there taken from make code, which is used with the microbit, and a similar sort of thing is done there, or a similar concept there of selection of forever, if the temperature is less than 18 degrees, then get the microbit to say too cold. So it's much easier to conceptualize and understand what is going on with the blocks and seeing it really physically happen than it is with quite an abstract concept of of using lists and things like that. And so students can see the impact of this straight away. They can hold the microbit up or the device up, and they can see if it is actually 17 degrees, and therefore it's giving me this output. So they can see the IPO, the input process output, occurring in real time, and that makes it instantly recognizable. And they are but in applying this, they're applying these abstract concepts, and it's less cognitively demanding. And that's really important, is that it's not just the fact that they're using blocks rather than a textually derived language. They can iterate really quickly, and I think that's one of the most powerful elements of using these blocks with all of the devices, is that you can rapid prototype really easily. And whilst some will dismiss blocks as sort of trivial, and it takes away some of the complexity, the complexity should come from the algorithms that they're applying to solve a problem. It should come from the computational complexity, not from how they arrive at the solution. In terms of whether they drag blocks across or they write it from scratch. Does the act of typing make a solution simplistic or not? It absolutely doesn't. It's about, are they applying computational skills in a sophisticated, confident manner, and an accurate manner, and if a student can come up with a solution to a complicated problem in 10 seconds using blocks, or in 5 minutes are using code because they have to type everything out and then deal with all the syntax issues and missing semicolons and whatnot, then you can get a lot more done in the time you have available to you using blocks. So I'm a keen advocate for PBL using these blocks, especially with younger learners. It just makes everything quicker, and we don't need to get bogged down in using textually derived languages. And that does become appropriate later on. We don't want to shy away from using programming languages, and especially with some of the tools that you see nowadays as well, you can convert from blocks to Python and JavaScript really easily, and you can flip between the two, and you can get them to start using text generative languages very quickly should you wish to. But starting with code, proper code, is not the best way to do it. But that's a bit of a tangent. And ultimately, really, using hardware allows students to relate the code that they're doing to the real world, and that's where this sort of intermediary step comes in. And I think that's it's really important for students to engage students when they're learning this sort of stuff. So next we're going to look at a bigger project, and the project we're going to look at is the oil spill cleaner upper. And now this, but before we get there, let's talk about the global goals as a series of contexts. Now these are a load of big problems that impact everybody on the planet, and these are something which all governments and companies are all striving to solve through what they do. And this is a really rich seam of problems that we can base project-based learning projects on, because they impact everybody. They are relevant to everybody, and they can be really engaging depending on what students are passionate about. So if you're looking at creating your own project-based learning projects, then these are a really good place to start and a really good way to engage your learners. So this is the project that we're going to look at, and this uses goal 14, so life below water, and it's all about sustainability, or conserving and sustaining the oceans and the marine resources. And so the context that we're going to give students is they have to create a autonomous boat drone that drags a sheet of smart material. Now this smart material has been designed that it can soak up oil like a sponge. And the idea is that they need to create a single one of these, although when these are going to be used in real life, there will be a swarm of them. And you can see straight away there that we can add in some additional complexity. So you could have, if you've got 10 groups in your class, let's say, you could get them as an additional challenge to make sure they act in a swarm and that they communicate with each other, so that they could clean up an oil spill over a large area autonomously, and they talk to each other whilst doing so. But that is maybe a step too far for the initial project. The initial project is getting the boat drone to actually first of all float, and then also be able to navigate a set area. So you can see the complexity of this project, whilst on the surface looks relatively simple, there's an awful lot going on underneath it that they need to think about. And the building element of this is can be quite interesting, because to test it you also need a body of water, which can be interesting in some classrooms, but it certainly uses the physicality of the problem in a really interesting way, and students really find this interesting. And it's not normal that they get to go and sort of throw computers into bodies of water and get them to move around. So this is a really good project, which is very scalable, and I've seen this used in secondary schools, grades 8 upwards, all the way through to undergrads, and you can add in additional success criteria to make it more complex. So this is the sort of setting the scene. This lays out the context for the learners, and you can see there's some examples of a boat drone there, which is similar, and these are obviously large scale robots that have been done for this, and you can see the scale of the devastation there from the picture on the right. So yes, this is why cleaning up oil spills is important. And you can really drive this home using videos of people mopping up oil off beaches or cleaning animals from oil and that sort of thing. So this is something that should tug at the heartstrings of learners, and they can see why this is an important thing to do. And here is the success criteria. So build a floating oil spill cleaner upper boat drone. So straight away it has to be able to float, and they have to think carefully about how do they do that. We don't want them getting the microbits or whichever device you use for this wet, and it has to start with the press of a button. So again, it's dictating here that you have to have a button in there somewhere, and that you don't want it to get wet. And then it's got to autonomously navigate over a set area. So they have to think about what does that mean, and that's relatively open-ended. So you can set this to whatever the body of water that you have. It could be, if you're doing it in like a small paddling pool, it could be just 30 centimeters by 30 centimeters. If you're doing it in like a swimming pool, for example, you could make it bigger. So it's scalable to whatever resources you have available. And then it should be able to drag a smart material, and that could just be something like a sponge or something similar that could simulate or model what this smart material could be. Now this smart material is real. And it does exist, so it's but obviously you won't be able to get hold of it for this particular exercise, but you can model it using a sponge. So let's break that down then. So we've got this problem set, and we want to explore how we're going to apply the input process output, or the IPO model, to this. So to start off with, we want it to start with a button press. So that is the the input that kicks off this whole process. And then the process bit of it is an algorithm to control the boat to go in a certain pattern. And you can see there, look, we've got a design for, there's the oil spill in the black, and this needs to go up and down and left and right to cover the entire thing. And then the output of that is the servo motor control. So obviously the algorithm needs to make the boat drone go up and then do a 90-degree turn, go a little bit further forward, then another 90-degree turn, and keep going and keep going and keep going. And so that is the algorithmic problem there. Now you could break that down into smaller steps. You could get them to sort of pseudocode the algorithm if you wanted them to, but that's enough of thinking about what the input is, what the process is, and what the output would be, and that allows them to start to work on that and then see the output in real life. And you can test this iteratively by sticking their boat drone on the water and seeing whether it does actually follow that pattern or not. So that's the way we want them to start exploring this. Next becomes the creation of the artifact, and you can see an example of one of them there. This was made out of balsa wood, and students used sheets of that, and they cut these up and attached the servos to it, and obviously to make sure that it floats. They stuck it together using glue guns, and this is the again the engineering mindset element of it. It's really, really fun for students to do this. You just have to make sure that you do a little bit of quality assurance when they're building these boats, so that you don't throw the electronics in the water, or that the boats are actually watertight. And so think carefully about the types of making materials that you give to your learners when they're doing this. And they can test this with a weight rather than the microbit itself initially, so just to make sure that it actually floats. Now, when they're doing this as a group task, we provide worksheets as part of the project for this, which gives them this stimulus. And you can see on the worksheet on the right, there's a link to a New Scientist website which explains how the smart material that we discussed works, and it even gives them the example there of the input process output table. And that's just a sort of this is part of that scaffolding. This is this is how you get started with this, and so you can give them that as a stimulus material, and then they can go away and start to design the rest of their product, and again keep repeatedly drawing them back to the success criteria, so that they can make sure that they're meeting what you're asking them to do. Now, when they're creating the model, you can, should you wish to, create like a mock-up on a model. Like, for example, these blocks will allow them to test the algorithm just on a microbit without needing to build anything else. So this uses the LED screen, and it gets the LED to go up, left, up, right, down, and then keeps going in that pattern. So you can sort of test just the shape drawing elements of it before you actually then implement that and refactor that into doing it with the motors. So you can do this without necessarily needing like servo motors and a control board and that sort of thing. So you can model this in a more simplistic fashion. To do this sort of properly, if you will, it's students have to think about the physics and the engineering elements of this as well. So there has to be a body for the boat, and they have to think about how they're going to drive the boat forward. So this idea of paddles. Now, some students may initially want to use like a paddle at the rear of the boat, but then how do you steer it? This has to be able to take a 90-degree right turn, and so they're going to have to think about how they're going to get the boat to turn. So you can see here in the model that we've provided that there are 2 motors, and you can connect these. In fact, on the version 2 of the microbit, you don't even need an additional board. You can power these straight from the microbit, which makes the whole process a lot easier and cheaper. But the most tricky bit really is mounting the motors to the paddles. And this is where some of this engineering mindset comes in, and this is where some of the making material needs to be considered. So how do they actually get these spinning servos to attach to the paddles? So most of these servos will have a sort of a bit of metal that comes out which has a flat side on it, so you can attach things to it, such as wheels, bits of wood, and you can glue it to it, and all sorts of different things. So it's worth exploring and make sure this is actually doable with the resources you have to hand. Now, if we look at the hardware needed here, as I say, there are different types of motors. You get different gearings on the motors as well. You definitely need a battery pack for this. You definitely need a board. You can see here we're using a microbit for an example, but you can do this with any other physical computing board as well. You also get these other expansion boards. This is an example of one for the V1, which allows you to control 2 motors at once, and I think you don't need that on the V2, I don't think. just think carefully about the hardware that you've got available. Now, this is why working in groups is useful as well, because you only need one set of this per group, and if you've got a group of, let's say, 4 students, then it makes the cost of these things much smaller. Some of the things you need to think about if students haven't done electronics before is they will need at least an understanding about positives, negatives, and voltage, and how to wire these things up. So making positive and negative go to the right ends, and depending on the expansion board you've got, making sure that these things are powered and is also grounded. So it's worth explaining at least briefly to students how to plug this together. Now, when I've done this with students in the past, we've shown them this picture so that we've modelled the solution with them, because this isn't really where the learning was coming from. The learning was coming from the algorithmic problem of mopping up the oil spill and dealing with the ambient conditions of the water, not necessarily from plugging it all in together. So you can skip past some of the more complicated bits just by providing model solutions to elements such as this. So they don't have to work it all out from scratch. But if you've got time and you want the focus of the lesson to be on the electronics, then you can absolutely do that by letting them explore this. So that's the oil spill cleanup project, and that is a really good exemplification of the project-based learning approach. And we've explored the theories that underpin all of this. We've explored an exemplification of how these theories are put into practice using the on-school program schema. And this entire approach of using EdTech and using physical computing is backed up by a lot of research. The Educational Endowment Foundation has produced a paper here, which I've taken some extracts from here, which shows that technology in a classroom in isolation does nothing. It needs to be used to enhance learning. And so just having electronics in a cupboard doesn't really do anything. They've got to be used in a way which is designed to eke out as much learning as possible from the learner, and is applied using a consistent and appropriate and well scaffolded pedagogy. And that's what we're trying to do with all of our resources. It's not just giving students technology and expecting them to learn through osmosis, but by crafting these well-designed learning experiences and then using technology to enhance that learning and make it more real and more tangible. I think that's the sweet spot of project-based learning, is using technology effectively in the classroom. So what are the implications of all of this? And obviously we've looked at some of the theories and some of the practice and all of this. Now, what do you want to take away from this? So really the pedagogical implications of this is that the context that you use have to be authentic. That's really, really important. And whether you use the global goals or something more local to you or based on a particular area of a subject, that's fine, as long as that students can relate to it and can use it in a particular way. The success criteria have to be thought about, and I'll look at the examples that we provide in our resources for good examples of that. But if you're designing your own versions of this, then think carefully about the success criteria, make sure that it is appropriate for the age range, and make sure that it is scaffolded should you need to. And then when you're designing the scaffolding, don't just give them the answers. Think carefully about how are you enhancing the learning journey and not just replacing it. One of the pedagogical restrictions, I suppose, is that this is resource heavy. It does take a lot of thinking about. Designing a good project does take time, and this is why we provide all of these resources for you, so you can just take these off the shelf and use them. Group work is an important factor with all of this. It just makes everything more cost effective, and you also get to see students express those Fullen's 6 C's and get them to work collaboratively and get more out of it by doing that. And there's also think about how can you assess this in terms of how this sits within the normal curriculum. You can assess project-based learning, and in fact we have a session later on specifically on this and how to assess it effectively. But obviously it's not best designed for formal assessment, and it's more, but you can use it to assess how students are engaging with the formal curriculum. And then there's the practical. Obviously you have to think about what hardware you're using and the cost of that, and whether you can actually get hold of it. Even at the moment, with all the supply chain issues globally, that can be quite difficult. So if we've covered briefly a lot of the elements there that sort of sit around what project-based learning is and what physical computing is, and some of the theories and some of the practical elements. If you want to learn more, please do go and have a look at our edX course, which is all about teaching with physical computing, and there's 4 courses there. Elements of today's talk has all been taken from course 1, which is Introduction to Project-Based Learning. But if you want more detail on any of these elements, it goes into a lot of depth in that course. And then there's the other 3 as well, which look at the sort of practical applications, which again we've looked at a little bit today in the second half, and then how to assess it, and then all about the soft skills and teamwork in course 4. So do check out that course. It's freely accessible on edX.org. So I'll wrap it up there. Thank you very much for listening to me today talk about project-based learning, and I hope this has piqued your interest in physical computing and project-based learning.
That's great. Thank you, Rob. Okay, so we've got some great comments and questions that have come in through the chat over the session, and we'll return to those in a moment. But for the time being, I'd just like to hand over to my colleague Surya, who will say a few words about feedback on the session.
Thank you, Nick. I have shared the feedback link in the chat box. I request all the participants to give their feedback by clicking on the link.
Great. Thanks, Surya. So yes, please do follow the link and complete the questionnaire so we can understand a bit about where you're coming from as teachers with respect to this content. And just whilst we're talking about housekeeping issues, just to cover another couple of points again, that a recording of this session will be made available on the training page on arm.community.com/ASP-India, which is where you'll have found your the registration link for this session. So in due course, a recording of that session will appear, and that link will be emailed out to you, along with a link to a certificate of attendance for this session as well. So a certificate will follow to all attendees. Okay, so we'll now move on to Q&A. So some great comments that have come through. I'd just like to start with one of the comments, which I think Rob has answered in the chat. But a very good point there from Sonia about teaching the entire curriculum through PBL would be quite difficult. And I think, Rob, the point that you've made in the chat there, and we tried to get across in our training, is that PBL is offers an important set of tools to teachers to apply as part of their teaching. So it may be once a term, it may be once every few weeks that you decide to do a PBL lesson, but it isn't there to replace your existing practice, rather to supplement it. Rob, further thoughts on that?
Yeah, I think you covered that really, really well. This approach is not designed to sort of replace your entire teaching practice. It's more to enhance it, and every subject is going to naturally have different areas where this will enhance learning more effectively. The STEM subjects lend itself to it really, really well, and we'll go through examples of that in the next session, where we take several examples of different subjects and look through those. But it can also enhance some of the other types of subjects as well, such as like music and performing arts, drama and geography and all those other ones. It's not completely quantitative, it's also qualitative, and it's you can use it can be used in lots and lots of very creative ways. And it's just a case of finding a context which is accessible by your learners, and then working out how to use technology to enhance the understanding of the curriculum area that you're trying to cover. And that's the creative part of this. There aren't projects available off the shelf that cover every subject at every grade using lots of different technology. That just simply doesn't exist. But you can create projects that do that in a very clever and meaningful way that really do enhance learning, and it links together in this sort of cross curricular approach, applying technology to different subject areas. And again, we'll go through several examples of that in a future session, which and hopefully that will inspire you to write your own projects using this schema.
Yeah, thanks, Rob. Actually, that addresses partly a comment that came in earlier about, will this be helpful with language teaching, which I think is more broadly to the point of it's the application of PBL and physical computing to other subject areas. I think it's interesting as well to reflect on certain topics such as data science being quite a generative area for cross-curricular work. So whether it's moving from a project where you're having to design a solution which perhaps involves data capture, this could be, you can imagine a buggy down a plane which might link into a physics lesson. The data capture, you then carry out the data analysis within mathematics, which involves, of course, coding too. So you can see that this approach really does work as there's a real potential there for cross-curricular links with other subject areas. So I think that's a good point. From a practical perspective, a question often comes up is whether a PBL lesson requires more preparation than a typical lesson. Rob, in your experience, what sort of prep work time is involved in getting yourself ready for PBL session?
Yes, that's a good point. I think it can be slightly more time consuming, especially when you're first starting out with it, because it's a different way of conceptualizing the planning process. Because you have to take into account the physical elements, the electronics, if you're using those sorts of devices, and that comes with the necessity for like PCs and internet connectivity and those sorts of things. So there is a little bit more to think about when you're doing these sorts of things, especially if you're writing a project from scratch. I mean, just using an off-the-shelf project like the ones in the ARM School program material, and from the micro course, for example, you can apply those just as quickly as any other type of teaching and learning resource. That's straightforward because it's all the thinking's been done. But designing these projects at first can be slightly more time consuming, but the more skilled you become at it, the more practice you have, especially when you know your learners and you know what hardware you've got access to and resources you have in your school. It can be take just the same amount of time. It's just a case of practicing how to structure the learning using the schema, and that at first can be tricky, but it does get easier over time. And as I've been through this journey many times, and it does get a lot quicker and easier as you go through it, but just because it's different, not so much that it's inherently more time consuming.
And a question has come up about the oil spill cleaner upper activity. It's probably worth noting that all of the contexts that have been discussed in the session today, you can find the projects within our resources on arm.school.com, where you will find a project book called Microcourse. So oil spill cleaner upper is part of Microcourse, and it's free to access and download if you want to start your experiment with PBL there. Rob's just put a link into the webinar chat there. So Rob, it looks as though you may have posted that just to host and panelists. So if you could repost that to everyone.
I don't think I can. I think Surya needs to do that.
Okay, Surya, if you wouldn't mind copy and pasting that into the chat, that would be great.
Sure.
Thank you. So another question, Rob, in terms of a large part of this session, we've done a real sort of broad overview of the educational theory that links into project-based learning. As educators, why is it important that we understand something of that theory before we go ahead and apply PBL in the classroom?
I think it's important to understand the theoretical underpinnings of the approach, simply because it justifies all of the different tools that we talk about, and understanding why you're doing it. I think is really important. As with all things, I think it's easy to skip some of the important steps out if you don't fully appreciate how the approach links together. And we're seeing this in where this has been applied in schools that we work with, where, for example, teachers might not think that some of the scaffolding is appropriate, or they apply too much scaffolding, and that sort of derails the entire learning experience for the learners because they're provided with the solutions, for example. So I think it's really important to see where all this is coming from, just so that you can be an effective practitioner. And like just looking at some of the theories that we've gone through today, you can see how the entire concept of project-based learning hangs together and how you can apply it to teach particular subjects well. And once you understand the why, then it's just a case of then practicing the how and structuring your own projects using the schema, and then applying that in anger in your classroom. So it's always a good idea to understand the why first. I don't think it doesn't necessarily need to do that. I think you could go in blind almost and use like the micropet, for example, without necessarily understanding all the theory underneath it, but it definitely helps. And as we're all practitioners, it's useful to understand the theory first. And this is a lot of the theory that we cover isn't necessarily new. It's typically taught as part of the teacher training courses, and it's just looking at it from a slightly different perspective and linking the practical to the theoretical. I think that's the important piece with all of this, is linking the theory to the practice.
Thanks, Rob. And just a reminder that you can, if you want to explore the theory and the practice further, you can go to edX.org and search for Teach with Physical Computing, and you'll find the 4 courses from the program, which I'll put a reminder on at the end of this session, which you can sign up for free. And there's further in-depth coverage of the topics covered within this session and other sessions within the 7 training webinars that we're running with CBSE. I think probably the final question, which really returns back to something that we covered right at the top of the session, is the link between PBL and technology careers. So we talked a bit right at the start before the main session started about STEM skills, but I wonder, Rob, after this coverage of the theory and the practice, whether you could reflect on that question.
Absolutely. I mean, part of the approach of project-based learning and physical computing is that it relates directly to the types of skills that industry want to see present in their employees. Just studying in a vacuum computer science or software engineering principles is a good start, and you see this with a lot of graduates. But all of the surrounding skills, all the soft skills, full on 6 C's that we talked about before, and that collaborating and that problem solving, that needs to be taught, and it doesn't naturally come to some people. And so practicing applying the theory in a real and cleverly contextualized way, it just enhances students' ability to be able to problem solve in these novel and interesting ways, and it just makes them more skilled practitioners of the subject, not necessarily just in computer science, but also in other subjects as well. And it's just sort of building that muscle memory of solving problems by applying the theory that we're trying to get across, and all of the classical learning theory supports all of that. So it's I think it's useful to get people coming out of education being able to practically solve problems using technology, and that's exactly the sorts of skills that industry are looking for, rather than just people that are sort of book smart without necessarily being able to apply it in a new and novel way.
That's great. Fantastic. So I think we will stop there with the Q&A. Thanks very much for all of your feedback. It just remains for me to close today's session. We would like to thank again CBSE, in particular Dr. Saha and Mr. R.P. Singh, for facilitating these sessions from the ARM School program. Just a reminder that you can find a recording. You'll be sent a recording and also your certificate for this, for attending this session, by email. And we do hope that you'll join us in the next session, which will focus on creating generative contexts that really engage your students within a project-based learning session. So it probably just remains for me to go back to our main course on edX.org and remind you that you can find that on edX, and it's free to enroll, where you can explore these topics covered within the CBSE training sessions in greater detail. On our website, which Surya has put a link to, you can also find all of our free to access resources and a link to sign up to our newsletter, which will where you'll get for each term an update on the latest content available through the ARM School program, as well as our training. Okay, thank you very much for attending, and I do hope we'll see you next time in next month's session. Thank you.